All right. Good afternoon, ladies and gentlemen, and welcome to the Albatross Spaceline's final presentation for MAE 4351 Senior Design. We'll begin with an introduction to the mission requirements.
Beginning with the history and background of space tourism, we start with the beginning of human spaceflight in the original race to space. 60 years ago, when the Vostok spacecraft carried Yuri Gagarin to an apogee of 320 kilometers. 40 years and 60 days later, Denis Tito would become the first person to pay for a private flight to the ISS on board a Russian Soyuz. A few years later, the X Prize contest was held to encourage the development of reusable and privately funded designs that could lower the overall cost and risk of space travel. With their Spaceship One design, Mojave Aerospace Ventures won the $10 million prize. This contest jump-started the space tourism industry that led to the founding of companies such as Virgin Galactic and Blue Origin, and is the basis of the research performed for the analysis of wing body spaceship UTA.
The specifics of the project are as follows. The vehicle must take off and land horizontally, undergoing rocket-powered flight to reach the Kármán line. During the vehicle's ascent, the 6 passengers and 2 crew members must not experience more than 3 Gs of acceleration, and during descent, this limit is raised to 5 Gs. The vehicle will be based at Mojave Air and Spaceport and will take off and land on its runway. A diagram of the vehicle's flight path is shown, and the key phases for the mission are takeoff and pull-up, boost, coast, apogee, reentry, glide, and landing. Albatross Spacelines is comprised of a group of 12 engineers, each with a wide range of specialties encompassing 9 separate disciplines. During this project, each member focused on 2 different aspects of the vehicle design process, with 1 member leading each discipline and 1 chief engineer to coordinate the effort. To begin your guide through the conceptual design of the vehicle, let's start with the discipline that oversees the process, synthesis.
Synthesis as a whole is the starting guide to aircraft design. Due to the wide range of vehicles that may be designed, there are many methods the synthesis discipline can choose. However, for high-performing vehicles, hypersonic convergence is the best method due to its total integration approach. This method keeps the vehicle performance goal constant while the aircraft is integrated in size entirely, unlike sizing components such as the wing and propulsion system separately in conventional sizing methodologies. This sizing process results in a set of feasible vehicles that make up what is known as a solution space. The end result of synthesis is to determine a design point from this solution space that can perform the desired mission. After literature collection and review was conducted, the primary sources for the hypersonic convergence method chosen are scramjet propulsion and future spacecraft propulsion systems and integration. Each source contributed valuable insight into the synthesis process. The hypersonic facilities research conducted by NASA and McDonnell Aircraft provided valuable data on previously conceptually designed vehicles that had the mission to fly at Mach 12 for a sustained period of time. With this data and the sizing process understood, the weight and volume budgets were formed. These equations make up the framework for the first multidisciplinary analysis, parametric sizing. Under parametric sizing, the weight and volume budget equations are solved simultaneously by equating the 2 functions. The equations are solved by iterating the planform area until both the weight and volume budget converge and produce a feasible statement. An initial takeoff gross weight result is also produced from this process. Based on the parametric sizing results, a vehicle geometry is then altered such that the geometry of the vehicle matches the converged data. Under the configuration layout process, an existing vehicle geometry will be chosen as the baseline geometry. Once the geometry base has been set, the geometry is modified to accommodate the size vehicle parameters as a result from the parametric sizing process.
The final step of synthesis is the configuration evaluation. This takes the data and geometries from the previous 2 steps and analyzes it through a flight phase analysis for the specific mission. At the beginning of this process, a specific flight path is chosen as well as the specific components of the vehicle weight. The center of gravity and inertias of the vehicle are also calculated here. With these values known, the flight phase analysis can begin. Each flight phase starts with a trajectory and performance calculation and ends with stability control. Shown here are the flight phases corresponding to the ascent of the vehicle from takeoff to the end of coast. If the vehicle can perform the ascent as required, then the descent calculations start. From apogee to landing, the vehicle must meet all requirements set upon it to be deemed feasible. If the vehicle can complete the flight, then a cost and safety analysis is performed. The purpose of this step is to determine if the vehicle is cost-effective and compliant with any FAA regulations that apply to it. If so, then it remains in the solution space as a feasible vehicle that can complete the mission. Shown here is a solution space that came from scaling the sizing parameters tau, fuel mass fraction, and thrust weight ratio. This is the overall solution space for the parametric sizing. As the synthesis process continues, vehicles will be removed from this solution space. This solution space shown contains 1,000 vehicles that were sized for the mission of space tourism. The minimum and maximum sizing values are shown to span from the platform area of 52 meters squared at 10,000 kilogram takeoff gross weight to a platform of 245 meters squared at 45,000 kilograms for a takeoff gross weight. With all these vehicles sized, let's now discuss the geometry discipline's impact on the solution space.
Thank you. The geometry discipline has developed a database of dimensional data for several existing wing-body spaceplanes. The 5 aircraft that have been selected for analysis are the X-Core Lynx, the Boeing X-20, Virgin Galactic Spaceship 2, C-251, and the Aerion AS-2. CAD models of each of the aircraft have been created, and utilizing CAD software in MATLAB, codes are created to A, scale the dimensions of each vehicle for a given platform area, and B, to generate a valid geometric solution space. The creation of the CAD models and database are aided by a literature review. Geometric data for each aircraft is gathered via several official documentation sources, and texts like Shiz, Nikolai, Raymer, Sadri, and Sforzum are helpful in determining the definitions for non-trivial geometry.
The geometry needs to match certain values of the sized vehicles, mainly the platform area and total volume. To do this, the wings are photographically scaled to the correct platform area. The geometry for the solution space shown belongs to the X-Core Lynx, and while the vehicle was small and on the lighter side for such a high-performing vehicle, it is not big enough for our mission. So, the fuselage height was increased such that there is sufficient room for the 6 passengers to enjoy their flight and their time in microgravity. The same height increase is applied to every vehicle regardless of the platform or volume. The width of the vehicle is then scaled until the fuselage and wing volumes add to match the total sized volume. This was applied to every vehicle in the solution space, and the vehicles that resulted in insufficient geometry were removed from it. This refinement removed 95 sized vehicles from the preliminary solution space using the Lynx space geometry. With this now reduced solution space, the analysis of each vehicle can begin to determine if they can complete the mission. Those that successfully completed the mission then have a cost and safety analysis performed and then reviewed. Of the 905 that remained after MDA-2, 235 vehicles were deemed feasible to complete the mission. This is approximately 24% of the preliminary solution space of vehicles. Of those that couldn't complete the mission, the vast majority failed due to either stability and control or performance issues. For stability and control, the main issues were losing aircraft stability or controllability at some point during the mission, while performance had the issue of not reaching apogee due to a lack of fuel or experiencing too many Gs during boost. Insufficient runway length is also a factor that resulted in some vehicles being removed. Compared to the X-Core Lynx and Spaceship 2, this solution space does contain values that are comparable to past vehicles designed for space tourism. The Spaceship 2 is a second stage vehicle, which results in its required weight and platform area needed being lower than a single stage vehicle. The X-Core Lynx was designed for a single passenger that did not experience microgravity as the passengers aboard our vehicle will, so its smaller values are still comparable, but not directly. Lastly, the design point for this solution space has a tau value of 0.1578, fuel mass fraction of 0.575, and a thrust to weight of 1.05. Again, the Spaceship 2 and X-Core Lynx values are there for comparison.
As mentioned, upon synthesis application of the MDAs to each aircraft geometry, 4 of the 5 aircraft are deemed unfeasible for the mission. The X-20 reported too few feasible configurations, Spaceship 2's feathering mechanisms add to unnecessary complexity, and both C-251 and AS-2 are too large to effectively complete the mission. Thus, the Lynx geometry is adopted, and after the synthesis sizing process, it's determined that the fuselage length, width, height, and platform area must be scaled up 150, 166, 270, and 302% respectively. The final scaled configuration of wing-body Spaceship UTA is highlighted in that lineup on the right. This figure shows a top view of the original Lynx geometry and wing-body Spaceship UTA. Unlike the Lynx that is meant to seat 2, our aircraft requires a far larger pressurized cabin to accommodate 2 crew and 6 passengers. The highlighted in purple is the allocation of cabin volumes for both aircraft, and the green shows the topography of passenger locations. The orange indicates fuel allocation, both primary and RCS, and the red indicates the rocket engines. So, more passengers, larger engines, and much more fuel, wing-body Spaceship UTA is bigger and far more powerful.
The purpose behind the weights and balance discipline is to produce the lightest aircraft that will engage in safe flight, select an appropriate aircraft airframe and material composition of the vehicle, determine the maximum takeoff gross weight based on the empty fuel, payload, and crew weight, and evaluate the center of gravity throughout each flight phase in order to produce a CG envelope. The primary literature used to develop the refined weights estimation methodology were Roscom's and Raymer's aircraft design text. The primary literature used to develop the center of gravity methodology is Sedre's aircraft design text. Key inputs necessary to begin the refined weights analysis will come from the geometry and propulsion disciplines in the form of vehicle geometry and engine specifications, respectively. Once a material type and structural layout has been decided, the weight estimations of the takeoff gross weight and empty weight can be calculated using empirical aircraft component weight equations that are based on historical data regressions of past vehicles that are similar in mission to that of wing body spaceship UTA. Afterwards, the center of gravity of the aircraft can be estimated based on the sum of the aircraft component weights in their respective locations from the aircraft nose. To ensure the methodologies created are feasible to the mission requirements of wing body spaceship UTA, the methods were verified using previous historical aircraft data. To rapidly verify the refined takeoff gross weight and empty weight calculations, a regression plot was generated with 8 vehicles that performed similar missions to that of our vehicle and produced a linear function that relates the two variables together. Using 8 surrogate aircrafts, a trendline of the empty weight based on the takeoff gross weight was constructed to provide a quick estimation of the empty weight. The methodology is based on Roscom's Class 1 weight estimation approach. Shown on the graph on the right, the Bell D-171, Skylon, and the X-20 are vehicles that match closely to the trendline generated from this approach, shown by the low percentage errors when compared to the trendline. The percentage errors of each of the 8 vehicles are presented in a table on the graph. To verify the CG methodology, the weight and geometry values of Spaceship 2 were implemented into the method and compared to its existing center of gravity values. The percentage errors between the methodology results and the existing Spaceship 2 values are presented below. After hypersonic convergence produces an initial takeoff gross weight estimate of wing body spaceship UTA, refined weight estimations based on Raymer's empirical aircraft component weight ratios were implemented to improve the initial estimate. Assumptions made when implementing the methodology were the inclusion of 2 rocket engines, the airframe composition being made of a multi-spar, multi-rib configuration, and the vehicle being analyzed assumed to have a supersonic cruise vehicle configuration. The refined takeoff gross weight of wing body spaceship UTA is approximately 14,429 kilograms with an empty weight calculation of 4,808 kilograms. The material composition of the vehicle is all carbon composite, a choice made to reduce the weight of the aircraft. On the right side, the empty weight breakdown is shown visually.
The landing gear must withstand the maximum weight of the vehicle when performing various maneuvers during the taxi, takeoff, and landing phases. Therefore, the design, location, and geometry of the landing gear are needed to further analyze the vehicle. The main literature used to develop the methodology in the IDA on the right is Sedre's landing gear design buildup. For verification of the methodology, the Lynx landing gear design, a retractable tricycle configuration, is analyzed and scaled to the geometry of wing body spaceship UTA.
The following images present the main center of gravity locations calculated at the empty and takeoff gross weight of the vehicle. The most aft and most forward CG locations were also calculated to develop the center of gravity envelope. As shown below, once fuel has been added to the back of the vehicle, the CG shifts aft, yet maintains within the bounds of the most forward and most aft CG locations. Now we will begin the flight phase analysis, starting with the takeoff phase.
The primary objective of the takeoff is to verify the vehicle can produce enough lift to have the vehicle actually take off the runway. In addition to this, the vehicle must also be able to have the elevons rotate the vehicle properly around the main gear. The primary disciplines responsible for this phase is trajectory performance, propulsion, aerodynamics, and stability and control.
Before the launch, our 2 qualified pilots initiate safety critical pre-flight operations in accordance to Part 37. This includes local notification by notifying air traffic control, hazard area surveillance within the vicinity of the designated spaceport and along the trajectory, collision avoidance on the ground or runway for traffic that may conflict with the day's launch, and meteorological data using FAA's aviation weather services to ensure there is no probability of impact by hazardous debris. Launching with the crew, Part 460 is followed for training, including the conditions for abort scenarios and emergency operations. They must be able to perform safety critical roles under intense pressure. In accordance to 460.9 regarding human spaceflight requirements, notifications of risks that come with space transportation are implied, and the human factors such as the physical stress for acceleration, vibration, and noise are Ascent.
The takeoff performance phase is imperative in the design process because it's responsible for sizing the wing of the vehicle. The main objectives of this analysis is to ensure that the vehicle is able to take off within the provided field length. The field length for Mojave Air and Spaceport is approximately 3,800 meters. Nikolai's takeoff methodology is used to derive an IDA for the takeoff performance, as can be shown on the right. Next slide. To verify the Nikolai methodology, this analysis is implemented in the Lockheed L1011 TriStar. The inputs for the vehicle are shown in the top right table. With those inputs, imperative takeoff parameters such as takeoff velocity and total takeoff distance can be determined. Those calculations were compared to verification data, and as can be observed, all the percent errors are at or below 1%. This gives way for the methodology to be implemented on the selected vehicle configuration. Next slide. Wing-body spaceship UTA is a significantly smaller vehicle compared to the L1011 TriStar. Hence, it was expected that the various takeoff parameters can be lower in comparison. As can be observed in the input table, the maximum lift coefficient is much smaller due to the smaller wingspan. Nevertheless, wingboard spaceship UTA takes off at a Mach of 0.21, which is well within the typical aircraft takeoff speed. The selected vehicle configuration has a longer takeoff distance of 1,773 meters. Nonetheless, the vehicle is able to take off with plenty of runway to spare. Now for the propulsion team to elaborate on the vehicle propulsion and the takeoff phase.
The methodology development for the propulsion and fuel systems discipline began by conducting a literature search from which 3 books were chosen for the analysis. The steps taken to design a propulsion system are summarized in the diagram shown to the right. 4 different engine configurations are used to verify the methods chosen. Next slide, please. After a thorough literature search, the RL10A4 was chosen for our baseline design due to its lightweight and high performance. 2 of these engines are necessary to fulfill the mission requirements. Next slide. A trade-off between chamber pressure and nozzle expansion is made as shown in the bottom right. Also, the tank pressures are calculated so that there is enough volume to withstand the amount of propellant needed for the mission. The results are shown in comparison with the Space Shuttle main engine in the graph at the top right. Next slide.
The second portion of the propulsion and fuel systems results mainly deals with the performance of the 2 RL10 engines utilized for the mission. The verification method used to obtain the speed and thrust profile of the RL10 engine had a percent error less than 5% and was used to analyze the propulsion system for the final sized vehicle. The thrust required at takeoff was about 56.9 kilonewtons, and seen on the thrust graph, this value is obtained about 34 seconds after firing the engines. Next will be aerodynamics to discuss the aerodynamic analysis for takeoff.
The aerodynamic analysis at takeoff focuses on verifying that the lift generated will overcome the takeoff gross weight of the vehicle. A methodology and IDA diagram were developed as shown with primary literature methods including the US Stability and Control DATCOM and Spencer. Next slide. The subsonic lift and drag wing pitching moment slope methods were verified using the Space Shuttle data and a developed database of delta wings, and most percent error values were less than 15%. For Spaceship UTA, the necessary aerodynamic values were, and it was verified that the wing produces enough lift for takeoff. Next slide. And now on to stability and control.
For the takeoff phase, the most critical part is ensuring the vehicle will be able to rotate the vehicle to the proper angle of attack required for takeoff. Survey was used as a primary methodology in developing the equations of motion, and DICOM was used to obtain the stability derivatives. Next slide. Using Cedray and also Colgren as a reference, the equation of motion for a delta wing configuration were derived and used to evaluate the necessary elevation control authority. The required lift and pitching control authorities are presented, and these variable was used to estimate the size of the elevons required based on the necessary pitching and lift control authorities by the elevon. The elevon control surface area was estimated to be approximately 11 meters squared with an elevon deflection of 15 degrees required to pitch up the vehicle. And now for the next phase.
The objectives of the boost phase involve determining the optimum trajectory that allows Spaceship UTA to achieve 100 kilometers with adequate thrust and stability. Furthermore, the loads experienced during this phase must not exceed 3 Gs. The primary disciplines responsible for achieving these objectives are trajectory and performance, propulsion, aerodynamics, aerothermal, and stability and control.
To develop the trajectory for spaceship UTA and analyze the performance during flight, the methods selected and verified were Vin's trajectory model and the Nicolai and Raymer performance analysis methods, the steps of which are shown in the IDA to the right. The Space Shuttle and X-15 were selected as verification vehicles because of their low aspect ratio wings and high altitude performance capabilities. Additionally, the X-15 weight was close to the goal weight of the spaceship UTA. Based on the closeness of the calculated and literature trajectory plots, the methods were considered viable for the spaceship UTA's analysis. Next slide, please. The top plot to the right shows the ascent trajectory taken by spaceship UTA, with the corresponding velocity profile depicted underneath it matching up to the trajectory. Inputs were received from the geometry, weights and balance, propulsion, aerodynamics, and the synthesis disciplines. The key boost characteristics can be seen on the slide. After constraint analysis, results dictated that in order to achieve the mission altitude of 100 kilometers, spaceship UTA must fly on a flight path angle of 60 degrees and requires a thrust of nearly 147 kilonewtons. With these characteristics, the vehicle achieved a propellant mass to total mass ratio of 0.575, which is in the average range for the vehicles of this size. The highest speed achieved was Mach 3.8 at an altitude of approximately 55 kilometers, which is also the point in time where the fuel of the vehicle was fully burned. This occurred 3 minutes and 20 seconds after takeoff. Spaceship UTA is also able to successfully remain within the 3G load limits specified in the mission requirements, where the maximum load was 2.75 Gs. The development of the load over the boost phase is plotted over the speed in the graph to the left. Now to propulsion.
The design challenges that the propulsion discipline will face during the boost phase are stated within the IDA to the right. For the boost phase, the CG location will change due to the change in orientation of the vehicle. Obtaining the rocket performance is of interest, and during this phase, the engine will cut off and a minimum sized engine will be obtained and analyzed to ensure that thrust requirements throughout the profile are met. Next slide, please. Through the same verified method from the takeoff phase, the thrust graph shows both the throttle engine setting of 50 and full throttle to ensure that the thrust requirement of about 142 kilonewtons are met. A minimum size engine with a mass flow rate of about 42.88 meters cubed per second was obtained and used to size the engine for the mission. The rocket efficiency was measured through a specific impulse value of 371.4 seconds, which was affected by the selected throttle setting. Next will be aerodynamics to discuss the aerodynamic analysis for the boost phase.
The aerodynamic analysis during boost focuses on supplying the drag and wing pitching values for apogee and stability calculations. A methodology and IDA was developed as shown. Next slide. Drag values were calculated after takeoff until the burnout altitude near 55 kilometers and again from the burnout altitude up to apogee. These values were used by trajectory and performance for determining apogee, and wing pitching moment curve slope values were used for stability assessment. And now on to aerothermal.
From literature review, it is learned that one of the limits of the flight envelope is aerodynamic heating. At high Mach numbers, an aircraft heats up due to the conversion of kinetic energy of the air into thermal energy. The increase in thermal energy is represented by the increase in temperature, which occurs due to the heat transfer from the air to the aircraft through convection. Next slide, please. The critical regions of the vehicle are the stagnation points and lower surfaces. Because of this, the aerothermal discipline is in charge of estimating the heating rate at the critical regions of the vehicle. The vehicle used for method verification is the Space Shuttle. Next slide, please.
David, I can't hear you.
Okay, for the boost powered ascent, US Air Force DACON was used as the main reference in obtaining the roll and yaw stability derivatives. Delta wing aircraft found within the references of DACON were used as verification of the DACON equations and methodologies. Errors would range between 5 to 15% depending on the wing configuration and other various required geometric inputs. Aerodynamic parameters such as the wing pitching moment and the coefficient of lift with respect to the angle of attack were obtained from the aerodynamics discipline. Next slide, please. The vehicle was found to be stable for the 3 stability parameters in the subsonic regime. However, as the vehicle crossed into the supersonic regime, the vehicle became less stable, yet still within the static stability requirements. This was expected and can be mitigated through an active control system as seen in numerous modern aircraft and wing body configurations. Now to the next phase.
In unpowered ascent phase or coast, the disciplines of trajectory performance and weight and balance ensure that the vehicle maintains enough momentum to reach apogee and that the loads remain below 3 Gs.
Once the engine shuts off and the vehicle enters into its unpowered coast phase, the weight after the boost phase was recorded. Because the entirety of the fuel was consumed during its burn time, the weight after the boost phase comprises only of the empty weight, RCS fuel, weight of the passengers, and weight of the crew, at a value of approximately 7,095 kilograms. The CG shifts forward approximately to the location of the empty CG location as the back of the vehicle has become lighter.
The coast phase begins once all the propellant has finished expending and the vehicle continues onto an unpowered ascent until apogee. Because the altitude is so high, the density and the dynamic pressure from here onwards is also zero. In the plot to the right, you can see the change in altitude with respect to the Mach number over each flight phase. What's important to note is the decreasing speed over the coast phase, shown in red. Spaceship UTA spends about 70 seconds during the coast phase. Next slide, please.
And now for the phase that everyone enjoys the most, apogee. During the zero gravity phase, Albatross Spacelines aims to maximize the amount of time customers get to spend in the zero-G environment. Additionally, it has determined how much fuel is needed for the reaction control system and the corresponding thrust forces. The disciplines responsible for these calculations is trajectory performance and stability and control.
This is the zero-G region of the flight profile. Spaceship UTA reaches a maximum altitude of 105 kilometers, successfully achieving the mission requirement of getting to suborbital altitude. The vehicle spends a total time of approximately 6 minutes in ascent to get to the apogee point. The vehicle maintains itself in zero gravity and allows passengers to enjoy a free-floating experience in the cabin for about 4 minutes. Next is stability and control.
As the vehicle coasts through apogee and experiences microgravity, typical control analysis methods may not be used. A reaction control system must be implemented to control the vehicle in the non-aerodynamic environment. The X15 is used as a reference to size the reaction control system and develop the equation of motion to obtain the necessary thrust force required and the fuel mass for the exo-atmospheric flight. As can be seen in the table, the errors verified with the X15 are low. Next slide, please. Here, the required thrust forces of the reaction control system for the 3 rotational axes are given, along with the minimum required mass of the system propellant of 200 kilograms. Next slide.
With the passengers strapped back into their seat, we can begin re-entry. In this flight phase, we ensure that wing body spaceship UTA is able to maintain a descent trajectory with an angle of attack high enough for it to reach back to the runway while keeping load factors under 5 Gs and remaining stable. Additionally, it is imperative to develop a thermal protection system that is able to withstand the high temperatures associated with atmospheric reentry. The primary disciplines that work on these objectives is trajectory performance, aerodynamics, aerothermal, and stability and control.
The trajectory and performance discipline will be in charge of determining key values that will be used by aerodynamics, aerothermodynamics, and stability and control disciplines. Griffin methodology was used to calculate the velocity profile and associated altitudes, and Reagan methodology was used to find the deceleration values and the time. Next slide. The re-entry analysis begins at apogee and will fall down into the range of 45 kilometers. This is mainly due to assumptions that were made within the chosen methods. A re-entry skip maneuver is done for the Spaceship UTA mission, which will allow for an increase in speed and will give a max Mach number of 3.57. This occurs at a higher altitude. And this also ensures that the G-force deceleration that is felt will peak at 2.3 Gs and will then have a second peak value. This G-force value is smaller than the allowable max 5G limit that was set by the mission, and the total re-entry time will be 423 seconds or roughly 7 minutes. Now I'll pass it on to the trajectory of the glide phase.
A trajectory and performance glide methodology was developed based on the primary literature sources, including Raymond, Roscom, and Nicolai. Next slide. The space shuttle was used as a surrogate vehicle to verify the accuracy of the velocity time and velocity altitude history methods, and most percent error values were below the 15% threshold, and the method was used to calculate the glide velocity profile history for spaceship UTA. Next slide. And now for the descent and glide aerodynamic analysis. The aerodynamic analysis during the reentry and the glide provides the aerodynamic coefficients for stability and trajectory calculations. The methodology and IDA shown were developed using primary sources from Kuchiman, Kui, and DATCOM. Next slide. Supersonic methods were tested using space shuttle data, and most percent errors were shown below the acceptable 15% mark. The reentry drag and pitching slopes are shown below. Next slide. During glide, spaceship UTA flies a constant lift-to-drag ratio equilibrium flight from 45 kilometers down to the landing approach, where it is operating at CL max before touchdown. And now on to aerothermal.
The aerothermal discipline is in charge of calculating heat flux values and surface temperatures during the descending phase. The calculations will then be taken into consideration when sizing the thermal protection system. Quinn methodology will be used to calculate the heat flux profiles experienced, and Fink methodology will be used to calculate the surface temperatures. Next slide. The heat flux profile for the lower surface of the spaceship UTA vehicle was calculated assuming a free laminar flow, which will give a max value of about 62 kilowatts per meter squared. But the most important heat flux value that should be checked would be the stagnation heat flux, which was calculated to have a max value of 113 kilowatts per meter squared. The max surface temperature that was measured for the lower surface of spaceship UTA was measured to be 880 Kelvin. With these major aerothermal forces, a thermal protection system will be required for this mission. But due to a carbon-based structure, the thermal protection system can be limited to the most vulnerable parts of the spaceship UTA. This includes the nose, the leading wing edges, and the vertical stabilizers. The material chosen for the TPS was a material called carbon-reinforced silicon carbide. The main reason that this material was chosen was due to the ceramic matrix composite, which gives it a low weight and high thermal conductivity. It is also oxidation resistant, which is a bonus. The total thermal protection system weight that will be applied to spaceship UTA is approximately 1,100 kilograms. Now on to stability and control.
The methodologies used for the reentry and glide phases were similar to that of the boost and coast phases, referencing DATCOM. The main critical challenge would be an aft shift of the CG and a high alpha reentry angle of attack. Next slide, please. The vehicle was found to be tending to instability during the high angle of attack for roll. However, using the reaction control system, this is mitigated similar to how the X-15 mitigated its instability during reentry. For the remainder of the glide phase, the vehicle became more stable in both roll, yaw, and pitch. And now to the next phase.
Finally, in the venture to come back home to Mojave, trajectory and performance must ensure that the landing phase that the vehicle approaches at a safe speed and does not stall. Stability control helps complete this objective by sizing the rudder to meet FAR Part 25 landing requirements.
The main objectives of the landing phase is to ensure that spaceship UTA can complete a safe landing at Mojave Air and Spaceport, and the main methodology that was chosen was Roscom, which will give different velocity and range values. Next slide. The main velocities that are calculated in the landing phase are the approach and touchdown velocities. The most important factors to ensure that the stall velocity will always be below these values. The stall velocity was calculated to be 33.38 meters per second, and the landing field length was calculated to be 1,146.5 meters. This means that spaceship UTA will be acceptable for landing at Mojave Air and Spaceport. Next slide.
Landing analysis for aerodynamics focuses on determining aerodynamic values on approach through touchdown. Similar methods were used to the takeoff analysis and applied to the landing analysis. Next slide. Produced at CL max during landing is sufficient due to the loss of mass from the fuel burned. The calculated aerodynamic values were output to the necessary disciplines. Now on to stability and control.
For the landing phase, the methodology was developed by referencing Cedre as the buildup for the landing equations of motion for wing body spaceship UTA. A subsonic vehicle provided by Cedre was analyzed to verify the validity of the equations of motion and resulted in a 5.75% error. The SR-71 Blackbird was also evaluated to get another reference for code validity in terms of a supersonic aircraft and resulted in a 14.2% error. It was decided that wing body spaceship UTA was to have all moving tail surfaces due to the supersonic flight capabilities and need for the vertical tails to be effective during supersonic flight. With this, spaceship UTA was evaluated to be able to perform a safe crosswind landing with a crab angle of 4 degrees and a rudder deflection of 2 degrees for a crosswind speed of 15 knots. Now on to the weights and balance discipline to discuss the weight change for the landing phase.
The weight of the vehicle at landing will be similar as the weight after the completion of the boost phase, as all the fuel has been consumed during its burn time. Nevertheless, the RCS fuel used for stability purposes has depleted after the apogee phase, leaving behind only the empty weight and weight of the passengers and crew members. The graphic on the right of the weight changes throughout each flight phase present these results.
With the flight phase analysis complete, we will now do a market and cost analysis of the vehicle.
The market and competition analysis begins with an IDA that was developed using primary literature by the Torrey Group, Futron, and Worcester. An analysis of the market size, and competition were all necessary. From the 8 markets analyzed, commercial human spaceflight proved to be the industry with the highest demand. Further research showed that this sector will be a high revenue generating industry with a lot of potential growth in the future, which was verified by space industry consultancy Northern Sky Research. Next slide. The next step was to calculate the potential market size within the suborbital commercial human space tourism industry using global wealth distribution data obtained from the Credit Suisse Research Institute for the year 2017. Individuals with a net worth greater than 1 million was used for the analysis. This pool of high net worth individuals was further reduced based on research studies and surveys conducted by Futron, in which the parameters seen in the lower left were all applied to the collection of wealth distribution data obtained. Next slide. Futron presented a total number of 6,842 participants in 2017 with a ticket price of $100,000. A number of 7,041 participants was calculated using the methodology developed, which presented a 3% error to the number reported by Futron. Applying this analysis to ticket prices in the range of $50,000 to $250,000, it was concluded that ticket price highly affects the number of participants the company can expect to see, along with the individual's fraction of net worth they are willing to spend on a single large discretionary purchase, as it is seen in the graphs on the right. Next slide. Design is not one size fits all, so there are a number of different configurations that a company can adopt within their design while still being able to achieve the same mission. From this, a number of companies can be seen in the table on the right. Virgin Galactic is the main competitor that Albatross Spacelines will be competing against, in which their traditional configuration of a 2-stage vehicle is utilized, which resulted in lighter vehicle weight. However, Albatross Spaceline's attempt at a single-stage horizontal takeoff and landing rocket-powered spaceflight vehicle proves to be highly competitive against Spaceship Two with the current technology. With a ticket price of $225,000 and a microgravity time of 4 minutes, wing-body Spaceship UTA also provides ample space within the cabin for the passengers to truly have a one-of-a-kind experience in zero gravity. Now on to Brian to discuss the cost analysis performed.
With a vehicle having been selected, a cost analysis is extremely imperative in determining if the vehicle is financially viable both for the consumer and the company. There are various methods to perform a cost analysis estimation of a vehicle. The 3 most well-known are the analogous, parametric, and bottom-up cost estimation. Each method has its own advantages and disadvantages, but the parametric method is the best option for this analysis due to the ability to predict costs due to operation changes. There are a plethora of parametric cost estimation modeling tools, as can be seen on the bottom right table. Unfortunately, many of them are unavailable due to ITAR restrictions. The transcost method is the best option due to availability and usability. Next slide. The transcost methodology was originated by Dietrich Körler, who published several versions of a cost handbook. This method was developed by examining cost factors of dozens of historical vehicles. As can be seen in the IDA on the right, the methodology is mainly a function of various vehicle weight components and cost factors. It uses the concept of man years to avoid having to account for inflation and the fluctuation of exchange rates. This method allows for the development, manufacturing, and operating costs to be determined. Next slide. The Transcost methodology was verified with Virgin Galactic's Spaceship Two flight vehicle, since this is the main competitor of Albatross space lines. As can be observed in the table, the methodology results in relatively low % errors, which deem the process to be reliable. Next slide. With verification of the Transcost method, the analysis was applied to the final configuration of wing-body Spaceship UTA. The development cost of Spaceship UTA is $1.5 billion, and the manufacturing cost is approximately $322 million for one vehicle. This is priced in the Spaceship Two, but was expected due to the higher weight and more engines. However, the operating cost per flight is lower because of the difference in propellant. Using liquid propellant is significantly less expensive compared to solid propellant. Next slide. With the cost calculations having been made, a life cycle analysis can be performed. The first figure on the bottom shows the decrease in manufacturing price for each subsequent vehicle. This is a result of the learning factor. The revenue plot shows that wing-body Spaceship UTA generates substantial revenue within the first few years, even higher than the Virgin Galactic system. With the ticket price per customer set to $225,000, Albatross Spacelines also generates a higher profit than Virgin Galactic. This analysis shows that a single-stage to suborbit system is financially visible, even more than the current two-stage system. Now I'll pass it to Bree for the final safety analysis.
Thank you. The objective of the safety analysis is to ensure that the vehicle, crew, and passengers, surrounding environment, and company personnel abide by regulations set in place to maintain a controlled area and a controlled flight for the intended mission. This includes applying the correct regulations for both ground and flight safety. As understood from Chapter 701 of Commercial Space Launch Activities, the goal is to safely opening the American people and their private, commercial, scientific, and cultural enterprises should guide federal space investments, policies, and regulations. Next slide, please. The research performed for the analysis tied in with the market analysis for understanding the current safety regulations, including documents dating to the initiation of the space tourism industry. These describe the possible risk factors and positive outcomes that came with the improvements of space transportation. Axel and Larson reports acknowledge the lack of government regulations in regard to experimental vehicles to promote the economic growth and entrepreneurship within the industry. Risk management guidance for launch and re-entry for reusable launch vehicles and the environmental policies and human factors were also taken into consideration. Next slide, please. The calculated and verified ground run from trajectory and performance coincides with that of Mojave runway to be used. For the takeoff flight phase, the launch angle limits were in accordance to Part 417-125, where the nominal launch elevation angle did not exceed 85 degrees. For the power ascent boost part of the launch phase, the gravitational force acting on the vertical plane of the body or amount of G's pulled was less than the limits of at which there is a potential compromise within the body. Next slide, please. Human safety at Apogee is what the 2-week training prior to the flight prepares passengers for. This point in the flight phase is where effects of radiation and microgravity come into concern. Solar or galactic cosmic radiation is considered, but for the mere time that is 4.5 minutes that is spent at Apogee, this does not imply that the passengers are susceptible to high radiation doses. The microgravity, however, can have musculoskeletal effects, disruption of bodily fluid, gastrointestinal effects, and also cardiovascular effects, which means that, unfortunately, Grandma cannot enjoy a ride on wing-body Spaceship UTA. Next slide, please. For the safety aspect included in the re-entry and glide phase, Part 450 was followed. It states that the permanent re-entry site must be declared, and per the mission requirements, Mojave Air and Spaceport is licensed and cleared for re-entry and landing. The G's pulled during descent are also lower than the limits proven to have minimal effect on the human body. For landing, the FAA acceptable level of risk approach for a horizontal suborbital vehicle within 80-kilometer radius is used. Next slide, please. With the confirmed parameters through the interdisciplinary analysis, the vehicle has proven its capability in providing a safe and efficient mission for its crew and passengers. The verification licensing used were based on the competitor vehicles that have gained approval and continue to carry out test flights using the FAA-granted experimental permits, which are Blue Origin and Virgin Galactic. Next slide, please.
Overall, the design point chosen by Albatross Spacelines is capable of completing the mission within the given requirements while also being cost-effective and following all FAA regulations. If this vehicle were to enter the space tourism market, it would undoubtedly provide competition to Virgin Galactic's Spaceship Two. With that, that concludes Albatross Spacelines' presentation. Thank you.